Anyways, so let's move on to. I don't remember if I gave it a name, but in the category of R modules. So if I take this M here, I think I was calling this guy N, and I'm taking an M in the category of right R modules. And I was looking at the functor that I could think of it as the functor that sends N to M, well, to this, or as the functor that sends M into this. So this functor is parameterized by M. We can think of it as the tensor product by M, or this functor which is parameterized by N, which we can think of it as a tensor product by N. Those two functors are right exact, and the left-derived functor of this, so the left-derived functor of Tm applied to M was the same thing as the left-derived functor of Tn applied to M. And, well, I'm not sure if you want to denote it. I think I denoted it by this in the previous lecture. And this is the complex. Well, so whose homology, if I look at the nth left-derived complex, this has a name, and people typically write this as Tor N R M N. So perhaps this star. So this is just a name for both of these groups that I've shown were the same. And you could compute either of them by taking a projective resolution of M in this category here to compute it this way, or taking a projective resolution of N in this category here, and then you just take the tensor product with M. So either way, you either resolve M or resolve N, you get the same answer. And this I didn't put a name, so this is going to be a name, and I'm going to call the Tor group that resolution. And today I just want to prove some properties of this. So as an example, and this is the only example that we care about, so example. This is already good enough for today. The example is the ring R to be Z, then R modules or right R modules are the same thing, and this is just abelian groups. Right, so, and the tensor product is just the tensor product of abelian groups. So now, for this ring, let's take a particular one. Let's take M to be Z mod P times Z. So that's one abelian group. And let's take N to be any abelian group. So what are the torsion groups? What are the torsion groups of Mn? So we can take so I want to compute this. I want to compute Tor star, the ring Z, M, N. And for this, I'm going to resolve M. I know I can resolve either of them. I'm going to resolve M. And we have an obvious projective resolution of M, which is given as follows. Z is over itself is free, therefore it's projective. And this sequence is exact. This is my M. And this is a free resolution of M, therefore that's a projective resolution of M. So I know that in order to compute this is the left-derived functor of tensoring by N applied to M. And the way we define this, by definition, this was, well, take a projective resolution of M, so that's this guy here. I'm going to look at this complex, and I'm going to call it P. So this complex P has Z in degree 1, Z in degree 0, and the differential in this complex is multiplication by P. So that's the complex P, which is a resolution of M. And, well, what did we define? We defined as follows. Take a projective resolution of M, apply your functor, which is tensoring by N, over the ring, and now take the homology of that. So that was the definition of the left-derived functor. Okay. So, well, this P tensoring by each side doesn't do anything. This is the unit of the tensor product, but the differential is non-trivial. The differential is multiplication by P. Therefore, this complex here, P tensor N, is the complex that has N. It has N in degree 0, this is in degree 1, and the differential is multiplication by P. So the homology of this complex in degree 0 is the co-kernel of this map, which is N divided by Pn, and the homology in degree 1 is just the kernel of the differential. This is just a notation, and P is the set of elements N in N such that P times N is equal to 0. So those are the guys that when I multiply by P, I get 0. And the homology in every higher degree is 0, because this P was 0 in higher degree. So as a corollary of this, we get that Tor N of Z PZ on an abelian group N is the same thing as, well, N divided by Pn when N is equal to 0. The P torsion when N is equal to 1, and 0 if N is bigger or equal than 2. Okay, so I want to prove a few things more about torsion, and then for that I need some more concrete examples of what limits were, what colimits were. So I avoided talking about filtered categories, but now we're going to need this. So let's remember what a limit or what a colimit is. So if you have a category I, there is always going to be a small category in everything I care, so these objects are going to form a set. And you have another category A that is always going to be abelian in all the examples that I care today. Then, if you give me a functor from this category I to A, I would say that the colimit exists. This is over this functor. I'll write it like this. The colimit over I of this guy here. This is what? This is going to be an object in the category A. Together with maps for every object I in I, and the set of objects of I is a set. And the class of objects of I is a set. For every element I in I want to have a map from this guy, F of I, which I'm going to start calling it AI, or perhaps I should say Fi. Well, it doesn't matter. It's going to be AI. So this is the definition. This is an object in the category A. And I want it to come with a map to this limit, to this colimit. Now, if you give me an arrow in the category I, then you can apply your functor f to that arrow. So this by definition is aj. And you have this arrow here, which is f of phi. And you have this map here. which I'm requiring to exist, and I will require that this diagram commutes. And finally, the universal property is that this guy here is universal for this. Namely, if you have any other object, let's say x, and maps from this guy to here, from this j to here, and for every arrow in I, this diagram commutes, then there exists a unique map this way. So that's the definition of what a colimit is. Now, colimits might not exist in a category. We will only care about filtered colimits. So I would say that I is filtered. Well, if the following two conditions, well, I again is a small category, objects from a set, and I'm going to require two conditions to be satisfied. If you give me any two objects of I want it to be a larger object. And I'm saying larger object meaning just there exists some other object in I and arrows that receives arrow from both I and j. And I'm saying larger because I'm thinking of an example. The example that I'm going to have in the back of my head is that I is going to be some partially ordered set. So this would mean, well, I don't know how to compare I and j, but there's some object that is larger than I and j. Now this is going to be completely automatic now for partially ordered sets, is that if I have two arrows between the same objects, so if I have two arrows between the same objects, let's say alpha and beta, then I will require that there exists a third object, k, and an arrow between j and k, such that the composition of these twos are the same, such that gamma composed with alpha is equal to gamma composed with beta. So any two arrows, might be different in I, but I can equalize them going a little bit further. Okay? So for a partially ordered set, that doesn't make any sense because there are two arrows. So either if two objects are comparable, then one is larger than the other one. I don't have more than one arrow between two objects. So I either have no arrows or I have one arrow between two objects. So this comes for free for partially ordered sets. This doesn't. I'm requiring that there exists an object that is larger than both objects. Okay, so a category satisfying this is going to be filtered, and I would say that I have filtered colimits if for any functor from a filtered category I to my category A, the colimits exist. Okay. Now, as a matter of names or notation, perhaps this guy here I'm going to often write as the colimit as I of the AIs. The AIs are canonically defined, are uniquely defined by this thing, and this is just a matter of notation. That's just the colimit of the function. Okay, so what we want to prove is that colimits are exact. So first of all, this colimit is this guy. I can view it if I fix the indexing category I can view this as a functor itself from A to, so this is the category of functors from I to the A to A. It's a functor. And before, perhaps we can rephrase this thing. Let's work out a little bit what is that thing. So here I'm requiring an existence of an arrow for every object of a form. So perhaps, right? Perhaps we can view this as a natural transformation between functors. Okay. So remember that if I have two functors between two categories, f and g, are functors between C and D. Then a natural transformation from F to G is the data that for every object here, X, then I have an arrow between F of X and G of X, alpha sub X. So this is my natural transformation alpha. So here, this object here is fixed. For all of these guys, I'm getting just the same object. So if I want to view this, but this f of x, so I can view this guy as perhaps I. And I have a map from f of, well, for each element I, x is equal to I have a map, well, from fi to, now I need to declare g of all of them to be the same guy, which is this co-limit. So I'll let you think about how to write the notion of co-limit as a natural transformation from F. Now, okay, let me give you a functor. Now let's fix I. And I'm going to produce a functor from A to the I. So first of all, let's, just in case I haven't defined this, so let's define this guy, A to the I. So the objects of A to the I as objects are functors F from the category I to A. And as morphisms are natural transformations. So if you give me F and you give me G from I to A, then a map from F to G is a natural transformation. We've checked that these guys, you could compose them and you have the identity and that forms a category. So that's the category A to the I. Now, there's a following functor that I'm going to call delta. This is the diagonal functor. There is a functor from A to this category of functors. So delta of an object X. Now I want to give you a functor that goes from the category I to the category A. So this functor is going to be the functor that associates to the object I in I, so this is an object here, an object of A, and it's going to be X. So this is on objects. It gives me, well, it needs to give me a functor, so I need to tell you what this functor does on arrows. So for an arrow from I to J, I need to get an arrow from X to X. And I want this diagram to commute. I'm not just going to give you the identity. Okay. So, all right. So now what I want is so this gave me on objects what these guys are, and now if you give me a map from X to Y, I have this delta of Y, which again, I'm viewing this as a functor, but again, functors, remember, it's what should I give you for objects? My view on functors in that board was delta of X I, and this is just X for every I. And now this guy here is delta of Y I, and this is Y for every I. And now let's suppose that you give me a map from X to Y, then you want to have a map from delta of Xi to delta of Y I and you were given a map here phi, well, you're just going to give me the same map here. That makes this guy into a functor. So now this delta became a functor from A to the I, to this category of functors. Okay, so claim. Sim. ¿Cómo que? ¿Cayó? ¿O?
Deixa eu ver no teu bolsinho.
Ah, morreu aqui. Alright, so claim. The full limit haven't proven that it's a functor. Let's check that it's a functor. Alright, so the co-limit is left adjoint to that. So let's prove this. There are several flavors to that. So first of all is that co-limit, again, I'm fixing I. I can take several functors, but the category I is fixed. So first of all, this guy is a functor. It's indeed a functor. Namely, if you give me two functors, f and g, and a natural transformation, what I want is an actual map from the limit under I of f to the limit under I of g, the co-limit. So this is an arrow, not a double arrow. So given a map between the functors, that's a map in this category. So that's a morphism in the category A to the I. I want to get a morphism of the functors applied to each one of these f and j's, which are the co-limits. Okay, so what is this alpha? Again, this alpha is a map from fi to gi, where this fi is f of I, and this is g of I. Such a way, so this is my alpha I, in such a way that if I have a map from I to j in the category I, then I have my fj, and I have my alpha j and gj, and this diagram commutes. So that's the datum, that's the alpha between f and g. On the other hand, this guy here, this co-limit here, came with maps from fi to that co-limit, and from fj to this co-limit, making this diagram commute for every arrow here. And this guy here came with maps from gi and gj, making this diagram commute. And this is just one object that came with maps like this. But now, since this diagram commute and this diagram commute, now this guy here comes with maps from fi to here and from fj to here, making all diagrams commute. So now by the universal property of this object, if I have one guy that comes with maps from fi and from fj, and for every arrow here this diagram commutes, then there exists a unique map this way. So that's the universal property of this guy being a co-limit. So that's this map. So this is the map which is the co-limit of alpha itself. Okay? So that's this map here. So I'm going to call this unique map the co-limit of alpha. So that's why co-limit is a function. Well, that's what it does on arrows. Now you need to check that it's associative and it has the identity and it preserves identities, but that I won't do that. So check that this is a function. So I just produce you what it does on objects and what it does on arrows, then it is a function. This assuming that the co-limit exists. So I'm here assuming that co-limits exists. Okay. The second claim is that this guy is left adjoint to delta. So now again, remember what it was to being left adjoint to delta. So this is that hom in the category A of some co-limit of the FIs to some object x is the same thing as hom in the category of functors of the functor f to this functor diagonal of x. And this is natural transformations between these two functors. So this in particular is a collection of objects of maps between fi and x for every I, and such that you get this diagram commute. Okay? So the adjunction is just the universal property of the colimit. That's the definition. So what I'm saying is for every object x with maps from fi and maps from fj making this diagram commute, there exists a unique map from the colimit to x. So that's the definition of the colimit by declaring it to be the adjoint to that function. Okay? So this implies, and this is a general property we checked, that if we have an adjunction, and this is honestly a different adjunction. I said that I didn't know any adjunction that wasn't hom tensor. This is an honest different adjunction. But what we said is that if we have an adjunction like this, then the colimit is right exact. Which is already very cool. This guy is right exact. This comes for free. So it preserves surjections and it preserves co-kernels. Because it's simply the left adjoint to a functor. So it has to be right exact. Okay. So the next one does not come for free, and is if the category A is mod R for a ring, so modules over a ring, then this guy is actually exact. And this is not true for an arbitrary abelian category, even if it's a co-completed category. So on mod R, co-limits exist, filtered co-limits exist. So that's one of the things that I'm claiming here. And moreover, I'm saying that this guy actually preserves injections. So it's also left exact. There are categories where co-limits exist, and this is not true. So for example, the category of abelian groups, let's not get there now. Okay, so let's prove this. Let's prove this thing. Okay, so for this, I'm going to construct explicitly the colimit. I don't know any other way, so I'll just do this. So the big difference between like arbitrary abelian categories and this kind of categories is that we can talk about elements in the objects. Which I couldn't do here. So here we just had abstract arrows. Now I'm going to use elements inside of objects. So let's say that you have your category I, which is a finite category, so the objects are just sets. I'm sorry, the set of objects is actually a set. And I have my functor into this abelian category A, which are given by modules over a ring. Okay? So I have a bunch of modules. So this functor is, I have a bunch of modules. Let me call this functor A, so that I have these functors AIs. So I have this collection. I is indexed by this, and this is inside of our modules, which is my abelian category A. And also, for every arrow from I to j, I have two modules, and I have an arrow between those two modules. So for every arrow from I to j, I have this arrow from ai to aj. So what I can do is look at the direct sum of all AIs in our modules, and let's look at the direct sum over all arrows. Again of AIs. So this is a much larger sum than this. Well, in principle, it's a much larger sum than this. So this one is summing over all arrows. In particular, I have the identity arrow here from I to I. Okay? Which is the only thing that I'm summing here. But the map here is that if you give me an arrow phi from ai to aj here, so this phi is an arrow from ai to aj. Well, this is silly. If you give me an arrow phi from ai to aj from ij, and you give me an element ai in ai, then there are two things that I can take here. I can take ai, which is in one of the summands, or I can take phi this is going to be the corresponding morphism from ai to aj that I get from the arrow phi from I to j. So I can take phi ij of ai, and this guy is in aj now, and I can take the difference between these two guys. So that's the map that sends ai in the component given by this arrow phi to this difference here. So this is not homogeneous. This has two components. This guy is in aj, this guy is in ai. And of course, if you take the identity arrow from ai to ai, and you take any element, this goes to 0. Okay? So if phi is the identity from I to I, this would go to ai, minus ai, which is 0 on this sum. Okay, so the co-kernel of this sequence is going to be the co-limit. So here's a claim that this is the co-kernel, that this sequence is exact at this point. So let's prove that. So would you? Okay, so, well, I need to check that every AI comes with a map to here. So what is the definition of this co-limit? Is that for every object I have some AI, and I have an arrow here, and for every arrow from I to j, I have some aj, I have an arrow here, and I get the sum. But now what is obvious is that for every object I have an arrow here, which is just the inclusion of this in the ith summand, and this guy commutes with for every object j, I have an arrow here. Well, this commutative diagram certainly fails. If I grab an element from I here, and I view it in this sum, and I have an element from j here, and I view it in this sum, certainly they are different. They live in different summands. So they are different guys. If I have my ai here, and I have my aj here, so I have an arrow here phi, ij. So this guy, since I want to check commutativity, needs to be phi ij of ai. But I map them here, this maps to this, and this maps to that. So now in this co-kernel, of course, these two guys are the same by definition. So I get this commutativity diagram. Commutativity on this side comes from identifying these two guys. Okay, so I have this data. And now let's say that I have another object, let's say x, with maps from ai to x and aj to x, then I want to prove that I have a map from this to this. Okay. All right. So, well, now I realize that I can take representatives from these guys. Right? So this, by definition, was a co-kernel, so this is a surjective map. And I have my AI. So an element here comes from some sum of elements here, and I need to tell you where those sums of elements is going to go there. So an element here, I pick any representative there. It's just a sum of elements AIs for some i's in I. So that's a representative of your guy here that you want to define what the image on X is. But you know what's the image of each one of these AIs is, because you have these maps. So you just take the image of those. So you take here the sum of these guys. I don't know, just put a name for this, tau. So this is going to be tau of AI. So that's where you would send this element A, whose pre-image is this sum of AIs. Okay, so now you need to check that this is well defined and this makes all the diagram commute. That the diagram commute is obvious because I've declared it to be such that the image is just the image of AI is that it's the same. That it's well defined means that it doesn't depend on the choices that I made here in lifting this. And the choices that I make here in lifting, they differ by elements in this kernel. And the elements in this kernel means that I'm identifying AI with the image on AJ by any arrow from I to J. And that's precisely what I'm doing here. I'm identifying AI here with its image, phi ij here of AJ, by saying that they go to the same guy. And that's precisely what the map X, the existence of X, is guaranteeing me. That the going from AI or going first to J and then to X are the same. So this does not depend on the choice of the representative here. Okay, so this claim, I think the claim was that this was the co-limit, is proven. Okay, so that gave us an explicit description of arbitrary co-limits in the category of R modules. In particular, the category of R modules is co-complete. Okay. But now I want to prove that it's actually exact. That this is exact. Okay, so the theorem is this guy is exact. Okay. So I need to prove that it's left exact. So I want to understand that it preserves kernels and preserves injections. So the only thing I need to check is that it preserves injections. So for that I need to understand what are injections. So remember, this is a functor from AI, from the category of functors to A. So I need to check that it preserves injections from here to injections here. In particular, I need to understand what are injections here. That's very simple to see. What is an injection here? So if you give me some F and a natural transformation to G, then a trivial exercise is to check that this is a monomorphism. And monomorphisms I defined abstractly for an arbitrary category. But in this particular case, this is a monomorphism if and only if the corresponding maps are monomorphisms in the abelian category A. So that's the data of having an injection. Okay, that this is an injection. My A is my abelian category. So what I want to check is that if I am given this data, so I want to prove that the co-limit of the FIs injects into the co-limit of the GIs. I've already proven to you that I have a map. I haven't checked that this map is an injection. We know that it preserves surjection and it preserves, preserves co-kernels because we've already proven that it was, by definition, it was the left adjoint. So the only thing that I'm missing to prove is this. And for that, I need to understand what is the kernel of maps into colimits. So, and that's where that description of the colimit, of an arbitrary colimit, is going to be useful. And again, this description here was not abstract. I've taken a direct sum, and I've taken elements and maps here. You could try to write this complex abstractly without using these AIs and see where you fail. So here I'm using an element AI in each one of in a summon. I'm telling you where it goes. So try to write this complex without using little AIs and big AIs. That wasn't really an abstract thing. That was really a for the category of ARM objects. All right. So the first lemma is this. So lemma. Perhaps before lemma, just perhaps an explanation. So here's an example of a directed category, of a filtered category. So the typical example of filter category is just this. The set is just the positive integer numbers. So I have 0, I have 1, I have 2, and I have one arrow between any two elements. I have an arrow between I and j, if and only, and it's a unique arrow if and only if I is less or equal than j. Okay, so I see this unique arrow from 0 to 1. I have a unique arrow from 1 to 2. Since this is a category, I have a composition. I have a unique arrow from 0 to 2, which is the composition of these two arrows. And the limit there is really just called the direct limit over Z. If you have a partially ordered set, so this is a totally ordered set, but you may have a partially ordered set. And remember, we are requiring that for any two objects, you have something that is larger than the two of them. But I don't have parallel arrows. So I don't need to worry about this situation that if I have two arrows, then I need to have a larger guy such that I can equalize these two. So I don't worry about this because I only have maximum a unique arrow. So any tree, any binary tree does this. It's an example of such a thing. And you can take direct. So all of these limits are going to be directed. These are direct limits. Namely, I do not need to worry about equalizing two parallel arrows. So the issue here is that this object here actually makes two things equal. When I have two arrows from I to j that are different, this thing is going to actually make two things equal. So when we take a direct limit of, say, vector spaces, right, on this diagram, what do you have? You have some vi, you have some vj, and you have some inclusion, say, from vi inside of vj whenever I is less or equal than j. And then the direct limit is just the union, in this case, of the vi's. It's just the union of the vj's. And the thing that we have in the back of our head of the vi's. And the thing that we have in the back of our head is that any vector here, v, belongs to some vi. For every v, in v, there exists some I such that V belongs to Vi. That's the way we think about direct limits. And the same thing for trees. If you give me a directed set like this, again, for every vector, it's going to belong to one of the objects that you have here. So that's the first thing that I want to do as a lemma. So lemma, suppose that you have a filtered limit. So now I'm going to deal with this, the subtlety of having two arrows that are parallel. So if you have a filtered limit, so let's take an element A inside of here. Then there exists some object I in your category and some AI in this object AI. Now let's put names. I don't remember if the book uses tau for this or phi or lambda. I don't remember. I think I'm going to use lambda for this morphism. From AI into the direct sum, and I'm going to use the same symbol lambda from AI, or probably lambda I, from AI into the direct limit. Okay, so by composition, this, and then just project into the co-limit. So there exists some AI in AI such that A is equal to this lambda I of AI. So same thing here. For every vector in the co-limit, there exists some vector space Vi such that my vector already lived inside of this Vi. Same kind of flavor. Okay. So by our construction, our element A comes from an element here in this direct sum. So there exists a bunch of elements, let's say A, J, a collection. There exists a set J inside of objects of I. So J is some I1 up to IN, where this I, J is in I. And this is a finite set because my sums are finite, such that an element AJ in AJ for every J in that set, such that A is equal to the sum of these AJs. And I'm abusing notation. I'm taking this guy is in this direct sum, and A is in the co-limit, but I'm saying, well, that sum, the image in the co-limit is A. Okay, so that's just the definition, that I can lift any element A here to a sum. So that is this. And the point here is that this sum is finite. Okay? And then the second thing is I is filtered. It's the same proof that you would do for vector spaces. Since I is filtered, there's a maximum guy. Well, there's not a maximum within J, but there's something that is larger than all of these AIs. So there exists some I with arrows phi Ji for every J in J. Okay? So there's something that admits arrows from every one of the little J. And this is just the fact that I was filtered. Whenever you gave me two arrows, you had something that was larger than the two of them. And since this set is finite, then I'm guaranteed to have something that is larger than all of them. Okay, so now, remember our construction of the co-limit. It was the same if I take J or if I take AJI. The image in the co-limit is the same. I was declaring, and for every time that I had an arrow J to I, the image of this object AJ, and if this arrow was phi Ji, I have here phi Ji of AJ. These two objects are equal in the co-limit because I'm dividing by the difference of these two. Okay? So in particular, this thing here becomes the sum of the phi j i's of a j's. And each one of these is inside of the same spot, ai. So this is my ai. And the image of this ai is a. Okay, so that's a simple name. But now I can ask a subtler question. In the case of vector spaces, this didn't happen. If I had this union of vector spaces from Vi, which is included in the next space, then the colimit was this union, and I had no, for each map from Vi to V is an injection. I have no kernel. So this is something new. That is a different kind of object that didn't happen for the direct limit, and is that the kernel from ai to the colimit of the ai's. So I have this canonical map from ai to the colimit that I called lambda I. This guy is going to be the union of all the kernels from ai to aj. And this is over all arrows that live over I. Okay, so the first thing to notice is that this side there is obviously included here. Namely, if you give me something in AI that maps to 0 in AJ, then this guy here to the colimit of the AIs, and this guy here goes to the colimit, and this guy commutes. So if I have that this guy goes to 0 here, then it goes to 0 here, just by the commutativity of this diagram. Okay? So this union is included here. And what I want to prove is the other inclusion the other way around. So if you give me something in this kernel, then it belongs to some of these kernels already. Okay? All right, so I need to describe this map from AI to that direct sum, to that colimit, and I want to check that is, so I want to take an element AI in AI such that when I view it in the colimit, then it's 0. Okay? Such that it's 0 in the colimit. Well, just take the image of that guy in this colimit. Okay, what does it mean to be 0 in this colimit? Well, being 0 in the colimit means that it is in the image of these things that I'm equating. That is phi ji. Well, I think I'm going to use that's right. So phi ji of aj is equal to aj in the colimit. So being 0 in the colimit means that so for x means exactly that. That if I could map this ai to some aj by some arrow, and I put them inside of the colimit, this well, phi aj, phi ij of ai, and then this guy is equal to ai in this colimit. Okay, so let's write this. And how am I going to write this? Okay, since it's 0 in this colimit, then what I know is that it is therefore in the image. So remember what we had. We had this sum of ai. This is like this. This was the colimit. I'm saying that I have something in the kernel of this map. I have some ai here that maps to the 0 here. Therefore, it comes from the image here. This was over arrows like this, and I had some AI like this. Okay? So my AI, which is an element in big AI here, that goes to 0 here, it has to come from an element here. So what is that element here? Well, an element here is a bunch of sums. I'm going to pick an arrow from I to j, and I'm going to apply it to some element in AI. Here, let's not mix this. This I is fixed. So here I'm going to take arrows from, say, j to k, to not be confused. And I'm going to put this aj, which is a source. And what I have is a bunch of arrows, j, k, and I apply this to aj. Okay? And, well, then I need to subtract the image, which was aj. So I have a sum like this. That is my AI. Well, but now, so my AI is equal to something like this, because, well, I'm saying that it goes to 0 here. So that means that I can choose this. So I can make this AI, I can replace it in the colimit, right, by the largest guy of all of these arrows to compare them. Like this. So this is happening in the colimit. Both of these guys are 0 in the colimit. So what I can do is just change this I by looking at a larger arrow than all of these k's that appear here to some, I don't know, AZ. To some phi I z AI. So this is going to be some AZ. And then again, whenever I have an arrow to k, since I have this z is larger, I'm going to have an arrow from this k to this z. So I'm requiring this z to be an object such that it comes with an arrow from I and from all the k's that appear in this sum. And I'm sure that that exists because my category I was filtered, and this is a finite sum. So then I can just replace all of them from AZ to be some sum of phi j z of a z of aj minus the sum of these aj's. And now this is an equality inside of AZ. Okay, but now this maps that goes, oh crap, I'm removing what I wanted to prove. Well, it doesn't matter. These maps that go from AI into this sum are injections. So this is just the ith factor. So since these guys are injections, so this proves that each one of these aj's now have to be 0. And that proves, so this proves that this each one of these aj's had to be 0. So that meant that this AI was in the kernel already. So this proves that each one of the aj's is 0. This proves that AZ is 0. And therefore, this proves that AI was in the kernel of this phi IZ. AZ was the image of I under that arrow from I to Z. So that checks that I started with this AI. I found a larger Z, larger than all the k's that appear here and, and the I itself. And I found that it was 0 there. So that proves the inclusion this other way around. Okay, so now I have a description of what is the kernel from each one of these AIs to the co-limit, and I have an inclusion of the co-limit saying that I can take pre-images in one of these AIs. Okay, so now let's prove the main theorem. So proof of theorem. I think I have enough time. Proof of theorem. So suppose you give me an injection. So now let's say that you have a functor f and a functor g, and this is an alpha and this is an injection. So we have the co-limit. Let me call these guys fi now over I, and we have a map to the co-limit to these gi's. And I want to prove that this is an injection. Okay? So this is here my alpha. The fact that this was an injection is the fact that we had this map injective. Alpha I is injective for all I. So I want to prove that this map here is injective. Okay? So I want to prove. Yeah, probably alpha is a bad idea, so let me call this the co-limit of alpha. So remember again how we constructed this guy, and now let's use explicitly what is the what is the description of both of these co-limits. So the way we constructed this was by some abstract nonsense that said we have this guy, now this is injective, and whenever we have an arrow, this is injective, and we had this maps to the co-limit here, and we have these maps to the co-limits here. And this came from abstract nonsense. But let's describe now explicitly why. How is this guy? This is a co-kernel of a direct sum of all these FIs. And I just said that whenever you give me an element here, A, then it belongs to some FI. I could find an AI in Fi whose image is A. So I can stop there. I can look at this AI that maps to A, or I can look at any guy that follows. So from Fj, I'm going to get the same guy. But at least there exists one Fi such that this AI is there. So now, how is this map constructed? Well, now I know what it is. So this guy is coming from my AI that sits here, and it maps to A here. And this AI goes to alpha I of AI here, and this guy maps to here. So that's precisely the image of A is going to be alpha I. Well, if I put a name to this, I think I was calling this guy something like lambda I. So the image of A maps to alpha I of, well, lambda I of alpha I of A I. And nothing depends on choices, because if I find any other j here that this diagram commutes, I can just take this whole thing. Okay, so now I want to exploit the fact that let's suppose that this guy goes to 0. So I want to prove that my A is 0. Okay? Okay. But that's on the nose. So this guy is injective, and this guy, so therefore, since this guy is injective, then this should have been in the kernel of this map that I just described. So since alpha I is an injection, then alpha I of AI is in the kernel of lambda I. Lambda I is the map from GI to that co-limit of the G's. And I just describe what is the kernel from the object to the co-limit. The kernel is the union of all the kernels to some GJs. So this kernel lambda I, remember that was the union of all the kernels from GI to GJ. So the kernel of lambda I for this functor G is the union over all arrows I to j of the kernel from Gi to Gj. So that means that this guy here, this alpha I of AI, belongs to the kernel of some, it is 0 for some Gj. So choose that j to be that. So this guy here is 0 here. Right? Because I know that it's 0 here, there exists now a j such that alpha I of AI becomes 0 here. Now this diagram commutes. So that means that if you take that arrow, this guy here is already 0. So that means that this AI was in the kernel of this map. So that means that this A was already 0. Okay, so this. Okay, so we spent a lot of time, but now direct limits are exact. So we proved the theorem that not direct limits, but filtered limits are exact in the category of R modules. So let's rewrite that theorem again. Theorem. R modules is a category satisfies AB5, and AB5 is the axioms that says that is co-complete. This category A is our module satisfy AB5, and that means A is co-complete, meaning co-limits exist, and this guy is exact. And this is exact for any filtered category I. Okay? It's exact for any I. Okay. So we just proved that theorem. And I haven't given you any other category that satisfies this AB5. So that's an extra axiom for abelian categories. This is not an axiom that will require abelian categories. So there are abelian categories that do not satisfy this AB5. And there are abelian categories that are co-complete that do not satisfy this axiom. Okay, but we have now that this co-limit is exact. So what's the beauty of exact functors between abelian categories? This is a trivial observation, but it's an important one. Observation. If you have a functor between abelian categories, an exact functor of abelian categories, then the functor, if you take the homology of F applied to a complex C, it's the same thing. Well, it's naturally isomorphic to F applied to the complex, to the homology of the complex C. Okay, so here C is a complex, is a chain complex in the category C. So this is just a bunch of, it's a graded object in the category D, or just do it for every n. So Hn is isomorphic to Hnc for every n. This is a trivial observation. Why? Because homology is built out of kernels, images, and co-kernels. You take the kernel of the differential, you take the image of the differential, you divide those two. And exact functors preserve those things. So homology is preserved by an exact functor. In particular, in a category A that satisfies AB5, homology preserves, commutes with colimits, with arbitrary filtered colimits. So as a corollary, homology commutes with filtered colimits on a category A when A satisfies AB5. Okay, so we know we have one category, which is our modules, and let's use this theorem. Okay. Notice that one particular case of this is the direct sum. Direct sum is a colimit. So homology commutes with direct sums. But this is a trivial example. This happens always. So direct sum is always exact by definition, and the same proof. Right? The simplified version proves that homology commutes with direct sums. Okay. So this doesn't require this AB5 condition. On the category A, you always have that homology preserves direct sums, but homology preserves arbitrary filter limits for particular categories, in particular for our modules. Okay, so let's look at now, let's go back to the beginning of the lecture and let's look at the torsion on abelian groups. I think I was using M and N. So I want to understand this. Remember, I proved something already. I've proven that we computed the torsion n over z modules for z divided by pz into any n. And this was n divided by np, by pn, for n is equal to 0, the p torsion for n is equal to 1, and 0 for n is bigger or equal than 2. Okay. So now the following lemma is trivial. An abelian group, every R module is a co-limit. R module M is a co-limit of mi's with finitely generated mi's. So you can study modules that are not finitely generated by looking at all the finitely generated submodules, and submodules of a fixed ambient module, they are directed. You can just compare them. One is inside of the other one. So that's a partially ordered set. Either one is inside of the other one, you put an arrow, and if they are not, you don't compare them. So that gives you a directed set. And the co-limit of that set has a natural object as a limit because all of these mi's come with an arrow to m. And that makes it universal. So that's just a trivial proof of this statement. But on the other hand, we know that homology commutes with colimits. So how did we define this torsion? So let's prove that torsion commutes with colimits. So this implies that torsion n z of m n is the same thing as the colimit of torsion n z of mi's n over R. Probably isomorphic, but there's a natural isomorphism between these two. So let's prove this statement. Okay, so here is the co-limit, and here I've taken the co-limit outside. So this is general for any for any right exact functor, f. So this thing here, so for any right exact functor f, and C has enough projectives, and it's co-complete, then let's take the left-derived functor of f applied to a colimit of some objects in the category C. So this was defined as the homology of the complex that you get by, well, take a resolution so this is the homology of the complex that you get by taking an f and take a resolution of the m's. But this guy is a resolution of the colimit. Now, f is right exact. F preserves colimits. And H preserves colimits. So colimits commute with both of these guys. And this is the same thing as the colimit of the left-derived functor. I think I used n. I think I used star of f applied to the mi's. So arbitrary colimits commute with left-derived functor of right exact functors. If my category is co-complete, so if these colimits exist, C has enough projectives, and I satisfy, and C satisfies AB5. So actually, let's remove this being complete because this is what was the condition for AB5. Okay, so in particular, in the category of our modules, this condition is unsatisfied, and therefore this holds. So I can compute the torsion of an arbitrary abelian group by taking the colimits over all the finitely generated subgroups of my abelian group. Okay, so now MIs, which is a finitely generated subgroup of M, well, it's a finitely generated subgroup. It's an abelian, a finitely generated abelian group. So MI is some Z to some power plus a bunch of Z's P1, Pn, C, just because the remainder theorem told me so. Okay, so those are the only finitely generated abelian groups. And again, the torsion n of Mi with coefficients in n, well, this torsion group is the sum, because torsion commutes with arbitrary directed colimits. In particular, it commutes with direct sums. So this is the direct sum, and I have the torsion n of z to the r n plus the sum over I of the torsion n z of z pi z n. Now this is 0, because remember that the left-derived functor of a right exact functor applied to a projective object is 0 if n is bigger than 0. Okay. We took a resolution of this guy, which was itself So it's 0 in degrees higher than 0, and that's why we get this to be 0. And this guy, we already know what it is. When n is equal to 1, this is tor 1. Well, this is equal to what? This is equal to the pi torsion of n if n is equal to 1, or 0 if n is bigger or equal than 2. Okay, so the tor n of m n is equal to well, something if n is equal to 0, that'll let you decide what it is because you know what it is. The tor 0 is the functor itself applied. Okay? And the functor itself is just the tensor product over Z. Okay? So this is just the tensor product of these two abelian groups. And if n is equal to 1, what you get is the direct limit, the limit over all primes of these pi torsions of n. And this is the torsion subgroup of n. And 0 if n is bigger or equal than 2, and this is if n is equal to 1. So the upshot is that, oh, sorry, I'm taking a particular m here. Taking a particular m, so this, that's false. I'm using here this, where I've chosen m to be q divided by z as a z module. So the finitely generated subgroups of m are of the form z divided by p z for all p prime. So the direct limit of those guys is this guy. So m is equal to the direct limit of z divided by pz. And I'm using this here. So let me write here q over z to make it precise. And here, yeah, it's not pi, this is np over all primes. Prime. So this, by definition, is a torsion subgroup of n. So theorem, tor 1 q divided by z, n is equal to tor 1 of n q divided by z. It's equal to the torsion subgroup of n. Subgroup of n for every n. And tor an abelian group. And tor n qz n is equal to 0 for every n bigger or equal than 0. Okay, so now the last one that is missing is tor 0. So the question for you is, what is this? Give me a nice description of this. I'll let you think about that one. All right, so I'm just in time. Yeah, I'm not going to ask you to recover classes. I am not going to be here on Wednesday, but then I'm not going to travel anymore until the end of the lectures. So I'll be here next Monday.